Okay, so we are going to start today the topic on species of structures. Let U be a finite set. So we are going to look at the topic on species of combinatorial structures. So a combinatorial structure is basically any kind of construction that you make on a set. Okay? So for example, if you have a set, let's say ABC, then you can make a graph on these three vertices, right? For example, like you can draw a graph with all the three forming a cycle, right? That you have seen, or forming a path, or just one edge and one vertex. Any of this is a graph on these three vertices, right? So you are basically putting a combinatorial structure on a set U, in the sense that you are constructing something out of this set. So the construction can be many things. For example, given a finite set, let's say U, as you see here, if you have the set U, then is, let's say, 1, 2, 3, etc. n, right? Then the structure alpha, let's say, can be a set, right? You can put a set structure on the set itself. A tree structure on the set, right? So you can take this and make a tree out of it by putting edges. You can make a cycle, right? Putting them in some order and then connecting the edges. You can make a permutation. So just take any permutation of the elements, you get a permutation of that. You can define functions on U, right? Elements, basically functions from end of functions, or a rooted tree, right? You can put a rooted tree, like you can define one node as special. One of the vertices, let's say 2 is special, then it has 2 or 3 children, let's say 1, 3, and 7. Then it has other children, etc. So you can define rooted trees. You can define poset structure, right? You can put a derangement, right? Derangement you have studied, or permutations which does not map elements to itself, right? There is no fixed point. Then you can define a partition, right? Given a set, you can partition it. So all these can be examples of structures. So I mean, there could be many more. So in short, we are just constructing structures on a given set. Now, here is an example of two different structures on the set A B C D E F, right? So A B C D E F is given, right? One set, and then we put a tree structure on this, right? So A to B is an edge, B to C, and B to D, B to E, and E to F. On the same set, I can put another structure, for example, C to A to B, B to E, E to D, D to F, and F to C, which is a cycle. So now, so these two are different type of structures, right? I mean, one can say that one is a cycle, one is a tree. Right? So you can now say that, like, I am interested in making only cycles, or you can say that you are interested in only making trees. So if you decide that we are going to have only trees, then we say structures of type trees. So I can say that for any type of structure that we are looking at, let's say F, then you look at all possible finite sets, right? So take U is one set that we consider, like 1, 2, 3, etc. n, or A, B, C, D, E, etc. Consider any such finite set, and then look at all possible structures of this type. For example, trees you are saying, right? So all possible trees you can make on this set of elements. Collect them together for all possible finite sets, this is called a species of the type tree. So now, similarly, we can do this for any other object. For example, I can say species of graphs or species of permutations, right? Which consists of all possible permutations you can make on all possible finite sets, right? Now, you collect together the set of all permutations, let's say, you can make on a fixed set, let's say U, right? So that I can denote by f of u, right? So f of u is the set of structures of type f on U. So if it is the collection of permutations, then it is the all possible permutations, right? Whatever is the cardinality of u, that cardinality of u factorial, many permutations are there on the specific set U. So that is the set of structures of type permutations on the set U, right? So f of u in general denotes the set of structures of type f that is made on the set U. Now, when we say a structure alpha belongs to f of u, right? We can write alpha in f of u. So that is it means that alpha is an f structure on U, right? So U is a set, and alpha is a structure of the type F that we are talking about, whatever species, right? Trees or paths or functions or posets or derangements, whatever we are talking about, that type of structure on U. Now, let us say that, like, you are looking at this examples of paths. Okay, A B C is a path, B A C is a path, A C B is a path. Okay, these be f structures. Okay, on the set ABC. Now, suppose we have a function f which maps, let's say, ABC to set 1, 2, 3. And the function f takes A to 1, B to 3, and C to 2, let's say, right? Now we know that if you look at the type of f structures on the set 1, 2, 3, there are corresponding objects there, right? But now what we can observe is that if for any bijection f from ABC to 1, 2, 3, right, we have a bijection from f of ABC to f of 1, 2, 3. So the corresponding bijection from f of ABC to f of 1 to 3. So in this example, for example, A to B to C, B to A to C, and A to C to B are there. And what does f of f do? That maps A to B to C to 1 to 3 to 2, because A is mapped to 1, B is mapped to 3, and C is mapped to 2 by f, right? Similarly, BAC goes to 3, 1, 2, and ACB goes to 1, 2, 3. So this is something one can intuitively feel, right? So whenever we have a bijection from a set U to a set V, we can think of a corresponding bijection from the set of all structures on U to set of all structures on V, where this kind of properties holds, right? Like, because F is taken by this, the corresponding let's say labels of these objects can be changed suitably to match the function. So this is intuitively clear, and one can in fact show it. We will skip the details, but let us look at one more example. Right, so you have this tree which is with a vertex x going to y, going to A to B and C, right? Then this can be mapped to let's say vertex q going to P 2, 3, and 4, and this map, right, between two structures, right, can be represented by, of course, the the bijection between the corresponding sets x, y, a, b, c, and p, q, 2, 3, 4, where x is going to q, p is going to y, right? Y is going to p, and a going to 2, b going to 3, and c going to 4, right? So, yeah, these kind of things are intuitively clear. Now let us give a example for defining species. So we have several ways of defining species. So let's say let us look at one example in detail. So we want to define the species G of simple graphs. So what is a simple graph? Simple graph is a graph structure on a finite set. Of course, we are looking at finite objects. Simple graph it's a graph structure on U, which means that there are edges, and the edges are two element subsets of U, right? Like unordered pairs of elements. Now we define the species as follows, right? So the structures on the set U I denote by G of U, right? Where G is the species, so therefore G of U denotes the all possible structures on the set U, which belongs to the which are simple graphs, right? Which is given by set of all G, small g, such that G is equal to, let's say, gamma comma U, where gamma is is a subset of two element subsets of U, unordered pairs of U. So one can see that gamma is basically the set of edges, right? And elements of U form the vertices of the graph, right? So we define the species by this. For whatever set you give me, this is the definition of the set of all structures on this. So therefore, since I can do it for any finite set, it tells me all about the species of graphs, simple graphs, right? So every graph can be generated given any set. I can make all possible the set of all possible graphs on this, right, by this definition. Now, what we can observe is that G is a simple graph on U, and G belongs to, right, G of U, and G is a G structure on U are all equivalent statements. And we observe that for each bijection which takes U to V, right, sigma map from U to V, that bijection induces another bijection, I mean another function, let's say, another map, G of sigma, right, which takes elements from G of U to elements in G of V, right? where small g, right, a graph is mapped to sigma dot g, right, where sigma is the bijection, right, from U to V. So this function G of sigma is called the transport of of graph, right? Basically, the graphs on graph structures on the set U is mapped to graph structures on the set V. So therefore, this is basically transporting structures, right, from on one set, which is defined on one set, to those defined on another set. Now, if if let's say a graph is given by gamma comma U, and that graph is one of the elements of G of U, right? The G structure on U. Then G of sigma, right, which is the transport of the graph G, right? G sigma of G, small g, is basically sigma dot G, right? Because that is what happens to G under sigma. And what is this? This is basically sigma dot gamma comma V, because V is the set that U is mapped to V. So therefore vertices are going to be V rather than U. And sigma dot gamma takes basically Now relabels the edges, right, with the correct numbers. So and that is given by this definition that sigma dot gamma is a set of all pairs sigma of x comma sigma of y for xy an annotated pair in gamma, right? So whenever there is an edge xy, right, uh, sigma of x and sigma of y will be the corresponding pair of elements that is going to make the edge in the transported structure. Now one can see that the transport is just a relabeling, right? From this example, one can see, and in general one have an intuition that the transport of structures is just a relabeling, and because of this, we should be pretty clear that if U and V are two sets, right, and then you are looking at G of U and G of V, right? G of U is the set of all G structures on U. G of V is the set of all G structures on V. Then, if U and V, if there is a bijection from U to V, then there must be a bijection from G of U to G of V, in the sense that G of U and G of V must have the same number of objects, right? If U to V there is a bijection, then it is kind of like intuitively clear why it should be the case. Therefore, one can feel that G of sigma, the transport of sigma, right, is basically a bijection also, and this also tells you that the cardinality of G of U, right, or cardinality of f of U for any species f, the cardinality of f of U only depends on cardinality of U. It does not depend on what are the elements of U, right? It doesn't matter what the names of the elements of U are, right? What are the elements of U? But if you have U and V, G of U and G of V depends only on cardinalities of U's and V's, right? U and V. We also see that because the transport is just a relabeling, we can also see that G of let's say tau composition sigma, where tau and sigma are two bijections, is basically G of tau composition G of sigma, and if you look at the identity map, right, on U, look at the structures G on identity of U, right? Like, I mean, look at the transport of G of identity of U. And this transport must be the identity in GU, right? The GU is the set of all G structures on U. And since, the transport function, the bijection sigma is just identity, the transport also must be identity on the corresponding set. When if this is not true, then we can see that like something will go wrong in our relabeling. So these are all. I mean, I am not going into the details of this. We want to finish this as a just quick review of this topic, just an introduction. So I will not go into details, but you can take it as homework to prove this. Now, more formally, the transport of a structure can be defined as follows. Let U and B be finite sets, and F map from U to V be a bijection. Then there is a function, of course, f of f, right, which f of f, which maps f of u to f of v, right, which maps f of u to f of v, called the transport of f along f, right. So for different bijections f, you have different transports, right? That is clear. Now, so this bijection, this function f of f, right, the transport of f should satisfy the following: that if you have two functions like two bijections f and g, and if you look at the composition f composition g, right, the f of f composition g is equal to f of f composition f of g, right? The transport also composes as the functions or bijections are composed, and f of identity of u is equal to identity in f of u, right? This is something we observe. So, in short, what we are saying about a species is basically is a rule. Okay, we can define species also as a rule that produces for each finite set U a finite set f of u. Right. This is something that we need to know. Right. When we say I am looking at species of all graph, you should know what are the possible graph structures on a finite set. Right. Without that, we cannot talk about the species. So, a species is a rule that produces for any finite set U, a finite set f of u, and for each bijection, right, from U to V, if U and V are two different sets, if for each bijection, you can find a function f of sigma such that f of u goes to f of v, where f of sigma satisfies the following conditions, right, which are called functorial properties. Okay. For every bijections sigma and tau, sigma going from U to V and tau going from V to W, right? You look at the composition T composition sigma, right? So what does T composition tau composition sigma does? It takes U to W, right? So f of tau composition sigma is basically f of tau composition f of sigma. Okay. So f of tau composition f of, because f of sigma, right, is basically the transport of sigma along sigma transport of sigma, which takes elements of f of u to f of v, right. Now what does f of tau does? It takes elements of f of v, right, to f of w, right? So therefore the transport must be composed this way. And for the identity on u, right, u going to u, f of id of u is equal to id of f of u. So these two properties, 1 and 2 here, are called the functorial properties. Right? So when we talk about categories and functors, in category theory, the functors basically satisfy these conditions. So that's so-called functorial property. So we are not going to go into details of category theory. That all comes in a specialized course on this. Now, as a homework, show that the transport of structures is a bijection if sigma is a bijection. So, for every bijection, the transport is also a bijection. It is intuitively clear, and it shouldn't be very difficult to prove also. Now, let me remark that one can observe that the notions of isomorphism, automorphism, etc., of F structures, whatever is the species, right, are implicitly contained in the definition of species. This is something that you can observe by the way we have defined these bijections, right? So the this all comes for free, right? Isomorphism, automorphism, etc., comes for free. Now, given let's say f, a species f and a set u, the cardinality of f of u, this I mentioned before, depends only on cardinality of u, right? Because what are the labels does not matter. Now we denote, there is an F structure on a set as follows, right? Let's say that ABC 1 3 is a set, and I am going to make some object of type F. So and like I'm looking at the species of not species, like the F structures on this set. I'm going to denote it the following way. So I write ABC 1 3 here, right? And then I put these lines, and then by this arc I mean that I am putting some F structure on this set. Okay, so it could be any of the structures. So therefore, this represents that we are talking about all possible F structures on this particular set. The same can also be represented by putting in a box all these points and putting just F to say that I am basically talking about all possible F structures, all possible structures that you can make on this particular set, which is of species F. And when I don't want to talk about specifically what are the elements, right? I mean, I can also just not write the set elements when the set is clear. I can just put this without the labels. And this also tells that, okay, whatever is the set having this many elements, I am going to put the structures. And these are just notation that we can use to describe type F structures on any set. Now, let us look at some examples. Okay, so a species E of sets. Okay, so we are talking about the species of sets, right? So given any finite set U, right? What is E of U, right? We are putting a set structure. So when I say E of U, it means that I am talking about structures of type E, right, which are sets on the set U, right? So I want to put a set structure on U. How do we put an set structure on U? Just look at the set U, right? So there is only one way to put a set structure on U, right? But basically, that set itself is the basically the elements, right? So elements of this E of U are the sets on U, right? There is only one set on U because U is a set, and I want to make a set structure using all the elements, right? If I am using a small subset of the elements, then that is not the set structure on U. It's a set structure on the subset. So therefore, E of U is just singleton U, where the element within this U are within the brackets are the objects of the type that we are talking about, right? So there is only one way to do that. That is putting U within a singleton. So that is the species of sets. Now species of elements I can talk about, right? Given a set U, I can talk about the elements. So that is E of U, right? So small e or epsilon is used for this. Let's say epsilon. So epsilon of U is the species of the elements of not elements. The yeah the objects of type elements of the given set U, and that structure on U, right? So we are talking about all possible elements of U. Now this forms the set of all these elements is the set U itself, because I am talking about the elements of U and forming the set, right? I get U itself. So therefore E of U is basically U itself. I can talk about the species of singletons, right? One element sets. So what is X of U? Given any set U, X of U is basically singleton U if there is only one element in U. If there is more than one element, I cannot put any structure, so therefore it is just empty. Right? So that is the species of singletons. I can define species by geometric descriptions now, right? So I can talk about species of polygons, right? Let's say P as follows, that P so I just define a set, let's say 5 elements here, put a structure and say that okay, this is a structure on 5 elements, this is a structure on 6 elements, etc. Right? So this geometric descriptions tells you how to make more polygons. Given any set, how do you make polygons, right? So that tells you how to do it. Therefore, this also can be used to define a species. Now, species of endo functions. Okay, so what is endo function? If endo functions are functions from a set to itself, right? So species of endo functions, which I denote by E and D, is basically the pair, let's say psi comma U, and that belongs to E end of end of functions on U, if and only if psi is an element of U cross U, and for every x, right? For every x belongs to U implies you can find a unique y in U itself, right? Y in U, and x comma y is in psi, right? So because psi is this ordered pair where x1 x comma y basically tells you where x is mapped to, and therefore y must be unique, right? So this is, this is the set theoretic description of the species of endofunctions. Now, as a homework, you can show that if sigma mass from U to V is a bijection, then the end of sigma, the transport of sigma of let's say psi is basically sigma composition psi composition sigma inverse whenever psi is an endofunction on U. So for any endofunction psi on U, right? It is transported to sigma composition psi composition sigma inverse by any bijection sigma. So this you can take it as a homework. Now another way to describe a species is by using the help of algorithms, right? Because sometimes it may not be easy to define an object. Okay, so you may be talking about, for example, the outputs of an algorithm, right? Some algorithm is there that can produce given a set, it can produce objects of a particular type, whatever we want, and these outputs are, let's say, objects of interest. So I want to talk about the species of all objects that is created by this algorithm. So given any finite set U, the algorithm produces a set of all possible structures of a particular type, right? Whatever it is, and I can now define the species by looking at the outputs of algorithms. What are the things that is produced by this algorithm that forms a species? So let be an algorithm that on an input, let's say set U, right, produces B of U, the set of all binary, let's say, rooted trees on U, right, where the algorithm produces binary rooted trees on U. Okay. Now, then the algorithm B can be used to define the species of binary rooted trees, right? For example, B can be like defining on the set U, right? A B C D E F is a set U, and produces some set of all structures, and in particular one of the output, let's say alpha belong to B of U, was the following, right? It is this was the output, right? So it says empty set comma B within bracket comma within bracket 5 empty set comma D comma empty set, and C then again empty set comma A comma within two brackets empty set F comma empty set then 5. Okay. Now then there is a comma and E comma 5. So the comma is missing. Now when we are talking about let us say this structure is a binary tree. If you look at this, the way to produce this is by by looking at this nodes, right? So each of these elements denotes nodes, and whenever a pair is there, that forms the edge relation. So 5 comma B basically becomes an edge from B to the empty set, which is represented by a box here. And similarly, if you follow through entire thing, you will see that this basically represents this binary tree. Okay. Now, and C will be the root of this. Okay, so you will see all these things if you work through the example more carefully. Now, as a remark, I want to say that a species is simply a functor, right? Let's say F, taking elements from B to E, where B is the category of finite sets and bijections, and E is the category of finite sets and functions. Okay, so a species is just a functor. Okay, if you're talking in terms of category theory. Okay, we are not going into category theory because to even define all these things it will take time, and we don't have that time. So if you are not familiar with that, just forget about it. Just a remark. The species is just a functor from the category of finite sets and bijections to the category of finite sets and functions. Now, some homework questions. Describe the transport of functions for the species E of sets, species E of elements, and species X of singletons. Okay. So basically, you have to see what happens whenever a bijection is given and what will be the transport corresponding. We for example gave the example of graphs, right? The species G of graphs, and then what happened to the transport, right? For any sigma, what was happening? We mentioned in the example that we are looking at with the graphs, right? So yeah. So here we said what happened to G of sigma, right? So what was the transport? So this way we have to mention what happens to the transport for each of the questions, each of the species in the question. Okay, second question is to define the species GC of connected graphs, the species D of directed graphs, and species PAR of partitions. So all these species you can define, right? Try in your own words, and let's see how good that is. That question is to define species INV of involution, species S of permutations, and species L of linear orders, okay, and species C of cycles. So we have already come across most of these things earlier, so I don't want to go into any more details of what are these things and all, right?